Okay, thank you everybody. Last talk of the day before the giveaway, so we'll try to get you there very soon. Okay, software ecosystem. So Jack talked about this in his presentation. RISC-V is the fastest growing ecosystem. I'm not going to stand here and tell you it's as big as x86 or as big as ARM today. But it's probably third and growing faster every day, more and more. But what I do want to tell you is that if you're starting to do software development on RISC-V, most likely the crucial pieces of software that you need for development are likely already in place. And so, it starts with having hardware to run these things on, but even before hardware, if you look at emulation, so SiFIve today has FPGA platforms that we can deliver to customers that support our processors and even processors in development. And in the very early days, this is how we engage with customers to demonstrate performance of our products and feature sets of our products. It starts with FPGA emulation. Additionally, on the simulation side, so there's many simulation tools that can be used. And these are very useful if you're just a software developer and you're interested in RISC-V and you want to port your project to RISC-V, simulation is the way to go. It's very low cost of entry. Open source software simulators like QEMU are readily available. They have great support for not just RISC-V, but the latest SiFive processors. And then there's a number of other simulation environments as well, depending on what it is you're trying to do. And I'll talk a little bit more about simulation towards the end of this presentation. But what's great now, and something I can talk about that we couldn't talk about 5 years ago or even 3 years ago, is there's many development boards that are out there that are based on SiFive, that are readily accessible, relatively low cost, easy to obtain, high performance SiFive development boards. So we have a very cute handboard. It's sponsored by Doctor Who and BBC. It's very easy to use. It has a graphical programming interface, very akin to the BBC microbit, very approachable and really targeted towards younger students and kids. Having said that, though, we also have other higher performance development boards, both developed by SiFive, like the HiFive Unmatched, but also with our partners, like the Star5 Vision 2, as well as the microchip PolarFire SoC board called Icicle, which is being demonstrated in the demo hall in the back. We also have newer development boards on the horizon with the HiFive Pro P550, and I'll talk about that in a minute. So very easily and accessible RISC-V development platforms that run at very high frequencies. They have application processors. They run high-level operating systems and so on. Let's not forget about IDE and tools. So again, we have two partners at this conference, so IAR and Green Hills. But there's a number of different IDE and tool partners that are available that have different offerings, each of them unique and special in their own way. But between the hardware platforms and the IDE and tools, the base level functionality of what you need to program a RISC-V core, it's there. It's been there for a long time. We've worked very hard over the past 6 or 7 years to help kickstart the ecosystem with the development boards, and that's really paid off. Now, as you move up the software stack, there's also what I like to call foundational software. So these are things like the compilers, libraries, key utilities that are needed to realize software applications. So GCC has had RISC-V support for a long time, but now there's even more foundational software that's available. So additional C libraries like Muscle, for example, newer programming languages like Rust, and so on. Now, as you move further up, it starts to get very interesting. So RISC-V has played in the embedded space for many years. So the non-Linux sort of embedded and real-time support is also very well and established. A lot of these projects have supported RISC-V for a number of years. Projects like FreeRTOS, projects like Artems, Zephyr, RT Thread, as an example. And so this kind of hits at the roots of RISC-V in the embedded space, where, you know, it's was the obvious choice for a long time in terms of customers choosing between RISC-V or some other ISA. Now, what's interesting is on the Linux side, you're starting to see more and more serious interest from the big players here in the distribution. So the Red Hats of the world, the Canonicals, the SUSEs and Debians and so on, whereby they have, most of these have unofficial ports of their distributions already running on RISC-V, and a lot of times these are running directly on SiFIve or SiFIve derived development boards. Now, as you get further up, this is where it starts to get interesting. So there's already lots of support for RISC-V out there, but this is really a big space, and there's no way we could have all the logos here, but this is also probably where we need the most help from people in this room to continue building and supporting RISC-V and optimizing for RISC-V. But even today, there's support for very popular projects. So projects like OpenBLAS, Docker, FFTW, Chromium, Ruby, you know, lots of very popular and pervasive applications that are already supporting RISC-V. And really, when we engage with customers today with processors like the performance cores, a lot of the discussions on the software enablement side are about understanding what customers require in this space. And so, you know, one thing to understand is the ecosystem in RISC-V is very large, but often for a given application, you don't need the whole ecosystem. You need a particular vertical or slice of that ecosystem. And oftentimes, the delta between what's needed and what's there is not as large as you might think. Now, as we get further up, so Andy did a great job talking about automotive and the automotive ecosystem. In the commercial space, there's lots of opportunities here for commercial software vendors to differentiate and start adopting RISC-V as the ecosystem and the semiconductor companies move to RISC-V. So companies like Electrobit, companies like Russell Tech are examples of people that we've been working with over the past year and a half as we start engaging the automotive ecosystem. Now, the big box here on the top right, so Android, you can see is a work in progress. So let's talk a little bit more about what that means. So we talked quite a bit in the earlier presentation about a lot of commercial momentum from key industry players driving Google to support RISC-V on Android. And I just had a good conversation about why Google would do this. And I think it's very important to understand that, you know, Google wants its operating system to run on devices. It wants you to do searches, right? Because that's how they make money, right? They make money by leveraging their software whenever you're running it on your phone and doing search queries and so on. Now, as ARM upsets their ecosystem, well, if they're suing their major customers and potential buyouts and things like this, those companies begin to look into RISC-V more seriously and engage companies like SiFive and other RISC-V players and start to realize that there's an opportunity there for them not just to engage in RISC-V and have more options and viability there, but also to have better products at the end of the day. And so as there becomes potential for commercial products to run on RISC-V and look good, it becomes interesting and motivation for Google to port their operating system to RISC-V. And that's exactly what they announced that they're starting to do at the RISC-V Summit in December. So they announced that they're accepting RISC-V patches into what's called the Android Open Source Project, or AOSP, where RISC-V will be a Tier 1 supported architecture. So what that means is all these patches go into AOSP, which becomes the upstream for all of the downstream operating systems that are derived from AOSP. So when you think of AOSP, you automatically think of Android that goes into your phone, but in reality, there's many different operating systems that leverage AOSP. So there's Android Wear on the wearables, Android TV on your smart TV, Fire OS, another DTV box, and many, many others. So SiFIve is very active in driving the AOSP community. We are engaging with the ecosystem, with the RISC-V Foundation to help enable and put plans in place on how to address Android enablement, because this is a very big problem and it's not going to be solved by one company or even the foundation, but by all of us. And so SiFIve is taking a leadership role in helping drive that. Now looking at SiFIve and what we develop in-house in terms of software, the RISC-V Foundation, RISC-V is built on open standards. It's rooted in open source. There's lots of open source projects that are going on around RISC-V. But in the RISC-V Foundation, there's over 3,200 members. Over 35 of these are pure play software companies. But even amongst the hardware manufacturers that are out there, right, the other semiconductor companies of the world employ many software engineers. So I'm sure there's many software engineers in the audience today that probably work for hardware companies. So there's lots of software that's being written for RISC-V. But SiFive ourselves, we deploy our software engineering resources, many of which are in Taiwan, and some of the key leaders from our software engineering team are here today. But we invest resources in areas that are crucial for enabling our hardware. So things like adding support for new ISA capabilities in the compilers. So GCC, LLVM, we contribute very heavily to these projects. Debug tools, GDB, bin utils, C libraries as well. We also take an active role in upstreaming support for new RISC-V capabilities in the Linux kernel. So we talked about RVA22 a little bit already, but this introduces a whole new bundle of ISA capabilities, and this is somewhere where we're investing our own software engineers into supporting. And this is for the benefit of not just SiFive, because we do have products based on these new ISA features, but the whole community gets to benefit from this. QEMU as well. QEMU is a tool that we use heavily internally to develop a lot of this functionality, and we do contribute a lot of this upstream as well. Now we do have SiFive software products that we deliver directly to our customers outside of these open source projects. And all of the tools that we deliver today are free of charge, and they don't have license keys or anything like this. So we try to make our software an enablement play for the IP as much as possible. Okay, so I talked about RVA22 in both presentations now, and I want to spend a few more minutes talking about it because I think it's very important. So I talked about the flexibility of RISC-V to configure the ISA up and down. But when it comes to the application processor market, so ecosystems like Android, ecosystems like data center, you really want to standardize on a good interface between your hardware and software. And that's what's going on with profiles and platform architectures that's being defined in the RISC-V Foundation. So it starts with the profiles that I talked about, RVA22, that's the application processor profile for this year, specifies a number of ISA feature sets, some that are new, like some of the cache management operations as an example, new capabilities that are being standardized in the foundation, that the hardware vendors have to implement, and software is beginning to target those features, right? So that they're talking to the exact specification of RISC-V that the hardware vendors are building. Now it's more than just instruction sets and register locations and memory maps and these types of things. There's also platform specifications that are being defined by RISC-V International, and the application profile is called OSA, and this specifies a more platform level view about what hardware should look like so that software becomes more portable. And I think the way to think of this is if you go back to the early ARM days, every specific semiconductor company that had ARM processors had their own BSP, their own fork of Linux that they had to maintain. And if you wanted to ship a device or a platform based on these products, you had to get this from the semiconductor vendor because they're the ones who had all the code. And you contrast this with x86, you can take any distribution of Linux, put it on a thumb drive, plug it in your laptop, plug it in a server, and chances are it's going to boot and work properly. We want to be more like x86 in the RISC-V world so that software just works and you don't have to think about it. And so what we're doing here with the platforms and the operating system and profile specifications is trying to get ahead of this and make sure that software early on targets these stable and defined specifications. So a lot of RISC-V development has been done on SiFIve development boards. I'd like to think this is one of the better things we did early on in the company. And I don't know if you're familiar with this saying, but in English we have this saying called chicken and egg. Which one came first? Nobody knows. In the software world, you don't want to write software for hardware that doesn't exist, right? What's it going to run on? In the hardware world, you don't want to make hardware if there's no software to enable it, right? So one of the things that we did early on, thank you, Jack, is recognize that this is an issue, and we bit the bullet and created the world's first RISC-V device in silicon in the HiFive 1 back in late 2016. So this really kickstarted a lot of the ecosystem development because then RISC-V became real. It's no longer a university project or some interesting research project. It's real. It's in silicon. People saw that and started developing for it RISC-V, and they did it directly on the HiFive 1. Now, recognizing that's the case, again, for the application class market, we developed 2 more application processor boards, and these were the world's first Linux multi-core capable RISC-V devices in silicon. So with the HiFive Unleashed, and then again in 2020 with the HiFive Unmatched. So with these, a lot of the distribution partners, like the Canonicals of the world and SUSEs, use these boards in their board forms to build packages for RISC-V. So in a lot of ways, enabling the Linux software ecosystem to run on RISC-V. And what's really nice about this is that if we hadn't released these dev boards in 2018, there wouldn't be any software to run on the cool, new, sexy P670 processors that we just launched last year, right? So in a lot of ways, we had to do these board developments to seed the ecosystem so that now that we have these really high-performing processors, there is a software ecosystem that's ready to accept them and to run on these platforms and can take advantage of them. Now we're continuing this, although with a partner of ours in Intel, which is one of our first partners for our first out-of-order core, the SiFive Performance P550, where they taped this out on a leading-edge Intel process, so Intel 4. So it's been in silicon since last year, and now we will make these boards available to the ecosystem towards the end of summer. So very excited to get this into developers' hands. It's developer-friendly board, so this is the soul of the machine for the HiFive the HiFive Pro P550. It carries forth some of the things that we had in the HiFive Unmatched, in that it's a micro ATX form factor. It has PCI Express expansion. It has the latest DDR, DDR5, 5600. It has M.2 slots. It has USB. It has gigabit Ethernet. This thing looks and feels like a PC, and that's on purpose, right? So that it's developer friendly. It's meant to enable developers. It's meant to enable the RISC-V ecosystem. It's out of order. It's high performance, over 2 gigahertz. So we're very excited about this board and can't wait to see what everybody in this room does once they have the hardware. So I'm running out of time, so I'll move a little bit faster. So SiFIve does have first-party software that we deliver to customers. We have an IDE called Freedom Studio. This is an Eclipse-based IDE. It really ties together all of the other projects that we have as well. Eclipse is very familiar. It's very extensible. We also have command line tools with Freedom Tools. So this is where we wrap together our LLVM and GCC distributions, SiFIve Recode that Johor talked about earlier, debug, simulation tools like QEMU as well. We have another deliverable that we call Freedom SDK for Metal. Freedom SDK for Metal is a set of example software packages as well as libraries and a distribution of free RTOS that runs directly on our processors. And it's very extensible in that the hardware can be configured in a lot of different ways. And we spend a lot of time making sure that Freedom SDK for Metal is also configurable such that you feed it the configuration file or the device tree, and it self-configures itself and the software to run on the SiFIve platform. And then finally, we have Freedom SDK for Linux. This is a SiFIve generated Yocto or open embedded distribution that's meant to run on our example platforms, and I'll talk about those platforms in just a second. But we think because SiFIve is an IP vendor and our IP goes into other companies' SoCs, Yocto is a good choice because it has a very layered approach, and it allows us to have very good Linux distribution that supports our processors, has our patches, our libraries, and so on. But then customers can build on top of that by adding their own recipes on top and leveraging a lot of the infrastructure of the Yocto project. So I kind of touched on this earlier. We have silicon development boards. There's new ones coming out. We have FPGA development platforms as well. So a lot of times when we engage with customers, they want to see the latest and greatest that we have before maybe it's available in some of these development boards. So FPGA platforms are a key means that we use to engage with those customers and expose some of these features as early as possible. And then, of course, we have simulation and emulation environments as well. And I think the next couple of slides touch on that. So because I'm running out of time, I'll skip this. We have lots of things that I already talked about and many different ways to run them. OK, SiFive evaluation platforms. So this is sort of a standard product, if you will, that comes out every time we have new cores. And what this is a hardware target in an FPGA platform. And usually these are commercially available off-the-shelf FPGA boards. So we partner with companies like Xilinx and Digilent to try to make these boards as accessible as possible. And then we have virtual platforms as well, usually based on QEMU. But what's interesting is the subsystems for these boards are the same. And the intention here is that the person who might want the FPGA platform has a different set of use cases and requirements than the person who want to use the simulation platform. But at the end of the day, if you want to get to a Linux environment, you want to share a lot of the code, right? And so we try to make it the same as possible so that an application that runs on the simulator can also run on the hardware platform. But the hardware platform is meant for the hardware developers who want to benchmark our IP, who want to understand if they run their kernels on our core, how much time it takes, that type of thing. And the software platform is really meant for the software developer who really just wants to get the application ported to the SiFive platform, but doesn't really necessarily care at that point in time the performance levels or need to do optimization. And then, of course, we have documentation that goes along with this that talks about what's in the platform in addition to the SiFive IP cores. Usually we wrap a number of peripherals in the subsystem to make it usable. And we have other SiFive peripherals as well. So for example, the WorldGuard controllers to enable demonstration of our security solution. 2023.03 is our next software release. So we release these every couple months. Our software releases really target the entire portfolio and not any one core, though we do have some packages that enable new hardware as it comes out. So as you can see in here, we have support in QEMU for the latest Panda products, which is the code name for the release that has the P400 and P600 products. But this adds support for RVA23, RVA22, and vectors and vector crypto and a lot of the new capabilities that are in those products. We also have a new release of the Freedom SDK for Linux, which has support for a lot of these things. It also has support for a lot of the libraries that we want to demonstrate as well. So things like OpenCV, FFmpeg, to demonstrate the new capabilities of the hardware. And then Freedom Studio, again, is our IDE, has a lot of the visualization tools, project management tools that the software developers need to write their applications for our platforms. On models, models are interesting because there's many different use cases for models. People lots of times ask for models, but you really have to dig into it and understand, well, what kind of developer are you and what kind of model do you need? So there's software development models. So I talked about QEMU a lot. It's really good for this. These guys that are doing software development, they want the model to run fast, and they don't necessarily care about accuracy. On the completely opposite end of the scale are the verification teams. So as we engage with the hardware companies and the hardware engineers, they want to use the model for hardware verification. But the verification engineers, they care more about accuracy, less so about speed or performance. And then there's everything in between. So, the point here is that requirements on models vary depending on who the developer is. And chances are there is no one model that can cover all of these performance points or all of these use cases. It's just not possible. So at SiFIve, we have a two-tiered modeling approach. One is a cycle exact model. This is based on Verilated RTL, if you're familiar with Verilator. So this becomes available around the same time as the RTL. That we have engineers who spent a lot of time optimizing the Verilator model to get as much performance out of it. But usually these models run around 10,000 instructions per second on a modern desktop machine. On the other side, I talked about QEMU a lot. So QEMU runs at hundreds of MIPS depending on the machine. And again, this is used mostly for software development. In both cases, what we've done is wrap both of the models with System C. So System C is a programming environment that allows lots of models of different types to be stitched together. And the goal here is to have similar interfaces between both the functional model and the performance model and the cycle model in order to enable our customers to drop either one into their modeling environment. So I'm really running out of time, so I'll skip these two and talk about our modeling partners. SiFIve has our own models, but we also acknowledge many customers have existing models and existing workflows, and we try to work with our ecosystem partners as much as possible to make sure that our customers can use the most familiar tools possible. So a lot of times we see customers who use Synopsys tools. They have platforms like Platform Architect as well as Virtualizer. So we try to make sure our models plug into these environments and that they're useful and functional. And then we also work with third-party modeling companies like Imperis, who's also been a very early and strong supporter of RISC-V. But we have many mutual customers with Imperis because Imperis have had great functional models for a long time now. And we try to make sure that our customers can continue to use the tools that they like. Okay, thank you.